Very good evening. In this video, we would be talking about the topic of gravitational potential energy. Now you see I have written 2 points, gravitational potential and gravitational potential energy, because I'm going to show you the difference between these two terms, and I have often found the students get confused between this. Also, while working out with gravitational potential energy, you might have come across to these two equations. One is minus G M1.m2 whole divided by R. This is the negative part. And also another one is the mass times the gravitational acceleration and multiplied by the height. My basic objective in this video would be twofold. First, to show you that these two equations will ultimately lead the same results. Second, what is the difference between gravitational potential and gravitational potential energy. And third, how we can derive the negative sign, not going through this, but something else. So let us just start with this. When we talk of gravitational potential energy, what we can tell over this is that gravitational potential energy, which is written with this term Pe equals to mgh, can also be written as the change in gravitational potential energy. I put a delta sign to denote the change. Pe equals to mass, which remains the same, g gravitational acceleration, which is 9.8 meters per second square, multiplied by height. And this is what will change the position, that is the height. And that is what I'm going to show you in a simple graph. Now say for example, I am drawing a graph over here. It would be this part, the x and the y axis. I'm drawing it nice and small because beside the equation it would be easier for you to understand. And if I place an object over here, this is an object. Right at this, potential energy equals to 0 because there is no movement in terms of height. So what I can tell you is that when I'm trying to move this particular object, when I'm trying to move this object on the top, say for example by 5 meters. So I'm trying to move this object at a height of 5 meters. This is the height. So what we will get from this is that the height changes. So once this delta h changes, so what I can tell you is that delta h equals to 5 meters, which is the change in the height which it moves, which automatically leads to the potential energy change is positive because it has gained a height. It has gained a height. What if I'm trying to drag the object or pull the object down by 5 meters? If we're trying to move this object down, then delta h, or the change in h, is also going to change to 5 meters, and essentially the potential energy would come to negative. This is by far one of the simplest explanation which follows by this. Change in height leads to change in potential energy. When it moves up, it has got a positive height, so it would lead to positive potential energy, and this is coming down, which would lead to the negative potential energy, right? So this is one part which proves with the change in height how potential energy is changing. Now for example, I take a different case. I take this equation minus G mmr, and I again draw a graph, and this time it would be a little bit different. The graph would be something like this, and this would be the negative part, which would come a little bit low. This will extend further. This is Earth, which is right at the below. Why I'm drawing this? Because I want to make things happen in a negative way, and this would be coming below. So let me find it out. So I draw 2 points. This is r, which is the distance, and it is going towards infinity, so I put it as an infinity sign. Potential energy at infinity comes to 0. Why potential energy at infinity is 0? I will let you know. I will derive this part, right? I will take 2 points. The first part is r1, and from r1 I'm moving towards r2. I'm moving towards r2. So what would be the graph which would come? So let me draw this graph for you. So this part of R1 would lead to something like this, and this part of R2 would come something like this, right? So essentially what it would lead to is that this one, R1, we call it as PE1, potential energy from R1, and this part we call it as potential R2, so we call it as potential energy 2. Now, for example, we take the potential energy at point 1, this is 1, to be minus 100, we put the unit as joules. And potential energy at point 2, we take it as minus 400 joules. Mind it, that's minus 400, although it seems to be bigger, but it is less in number. Now, when I am moving from R1 to R2 in this direction, I'm moving in particular in this direction. That means if I consider this to be the center of the earth, I'm moving towards the earth, right? So I take the change in potential energy, PE, equals to final minus initial. This you should not miss. This is final minus initial, right? So I can take it as potential energy calculation for PE1, 2, because I'm moving from 1 to 2. So I can put it as change in potential energy from 1 to 2. This part would be final minus initial. So I'm moving from PE2, this would be PE2. So PE2 to P, this is from R1 to R2. So the final is minus 400. So I take it as minus 400. Minus the initial where I am, that is R1, is minus 100. I am omitting the figures or the points right now. Put it in braces. Let me write it once more for you. Minus 400 minus 100 joules. So what it would lead to, it would be minus 400 minus plus. So it would become plus 100, and finally it would become minus 300 joules. Minus 300 joules. So what is the point which I am trying to make? The point that I am trying to make is that given a position, given a point R1, when I am moving towards the surface of the earth, I am getting a potential energy which is negative. Did you see the same thing which happens when I'm moving away towards the earth? Potential energy is getting negative. Now we need to see that what will happen if I take a value when I'm trying to move away from the earth. So shall I draw another graph? I think this is nice and fine. So in this case, I will just take another direction. I'm moving from R2 to R1. So I'm moving from R2 to R1. So from here, my now direction is this, that is away from the center of the earth, right? So what I can do is that I can calculate that it is, so I'm moving from where? From R2 to R1. So my calculation initials would be P21, right? So I take the potential energy for PE21 would be again final minus initial. So what is my final? Final would be I'm moving towards R1, right? This direction. I'm moving now towards this direction, R2 to R1. And what is my R1? Minus 100. So let us put the values what we have got. Minus 100 joules minus of initial where I am, it is minus 400 joules. So what it would result to? It would result to minus 100 plus 400. And the end result would come to plus 300 joules. Right? So what the point that I tried to make is that right at the beginning of the video, let's see whatever equations that we are taking, whether it is the gravitational potential energy of this part or this part. When I'm trying to move an object right from this part to above, that means I'm moving it away. When I'm moving it away, that means I'm gaining the positive potential energy. When I'm moving towards the center of the earth, I'm getting a negative potential energy. And isn't it happening is the same way? When I'm trying to move an object, mind it, from this position to this position, that means I'm moving away. That is P1, 2, right? I'm moving it away, I'm getting a negative potential energy. That is, I'm getting a negative minus 300. And what I'm trying to do when I'm moving from R2 to R1, that means I'm moving away. I am moving away. See, I'm moving away. It gets a positive 1. I get a positive 1, 300. When I move negative, I get a negative 1, minus 300 joules. So the first part of the video essentially shows that how with the change in height, positive and negative, the gravitational potential energy changes. And here also, by using the simple equation final minus initial, we are getting a negative and a positive potential energy depending upon the way or the direction in which we are moving, away or towards the center of the earth. The second part of my video would be something different. What I would like to show you is this. I'm going to draw the surface of the earth, and I'm going to take an object away from the center of the earth, and I will try to get another form in which I would like to show you the gravitational potential energy. So let me draw this one. So this is the earth, which is obviously wrong, which I am drawn. It is an oblate spheroid, but never mind, for the knowledge part this is fine. We have got a radius, I mention it as small r. This is an object which is sitting right on the surface of the earth with mass m. What I'm trying to do over is that I'm trying to take this object away, far away towards infinity, right? Away from the earth to some space where coronavirus is not there, and this is the radius. So what is happening is that the earth has got a gravitational attraction which is moving towards the center. I am putting a force which is in this direction. I'm trying to put it away from the center of the earth, right? Now we know, I am not going towards the the derivation part. We know that the work done, which is from the center of the earth to take it away, that is, if I call it Pe, that is the work done, would be equal to G M whole divided by R. We know this. If you are interested, you can watch out my another video in which I have deduced this part. So we can call it Pe or we can call it W. W equals to capital G M whole divided by R. Now this is from the surface S to infinity. So this is the work done from the surface of the earth to the infinity, right? Now you might ask me, why potential energy? This is the potential energy which we can put it as 0. Why potential energy at infinity is 0? It is nothing an assumption. It is pure mathematics. Simple yet pure mathematics. Now when we are taking the potential energy at the surface of the earth in this equation, what happens when I push this object far above? So the radius or the length will become infinite, right? So I put this equation R equals to infinity. And then if I substitute that, Pe equals to G, which we know minus 6.67 multiplied 10 to the power minus 11. I'm not going to the detail. So whatever the values at the denominator it happens, say for example x whole divided by the infinity, that is R. So anything divided by infinity leads to 0. And that is why the potential energy at infinity is 0. The reason also is that when two masses are far from the earth, there is no gravitational attraction which is happening between these two things. Now, considering that this is the gravitational potential energy of the mass when it is on the surface of the earth, and given the value that potential energy would be 0, what would be the potential energy at this point? We know that the work done, that is, I am pulling this mass away from the center to infinity, equals to this. And at infinity potential energy 0, we have just shown this. So what would be the potential energy in the surface of the earth? Obviously this plus something which would lead to 0. So that automatically leads to potential energy equals to, if this is plus G capital M whole divided by R, plus it should be a negative G capital M whole divided by R braces. Now this is what I'm trying to show you. this is exactly what it leads to. So any value which I'm trying to put over here with a positive sign will lead to something which will lead to infinity, where potential energy equals to zero, and that is the reason that gravitational potential energy comes to be negative. Because if I don't put the negative, it won't cancel out and it won't lead to zero. Now, just a few points, that if I take a mass of 10 kilograms, say for example, and I am just substituting the value of 10 kilograms over here. Now what I will do is that this 10 kilograms will be substituted over here in this equation. So what will we get? We will get W equals to capital G M multiplied by 10 kilograms whole divided by R, right? Again, if I put it 20, 30, whatever. Now, what I want to show you is that what is the unit, what is the value per unit mass, per unit. I put this word as per unit. So I need to put the per unit. So I can put it here as W equals to capital G M multiplied by 10 kilograms whole divided by R whole divided by 10 kilograms. Otherwise we won't be getting the per unit. So 10 kilograms get cancelled out. What we get is W equals to capital G M by R. And this is our gravitational potential. This is what we called gravitational potential. So I can just put the initials as GP. This is the gravitational potential. Now you see, if I put 20 kilograms, again it will cancel out. 30 kilograms, again it is going to cancel out. So this part is a fixed unit, right? So this is the gravitational potential. And what is the gravitational potential energy? We can put it as capital G M multiplied by mass of the body, that is 10 kilograms here. So we can put it as M, which is 10 kilograms, right? Whole divided by R, right? So we can tell it in other words that gravitational potential energy, if I term it as GPE, just to tell you, in other words, is gravitational potential, that is GP, this part, multiplied by the mass of the object. Mass of the object. So essentially what we get from here, if we take this part only, GMR, this is the gravitational potential and this is the gravitational potential energy. So just to summarize in a way which I have put it in a different manner which you can quickly recon. So you see PE equals to mgh 0.1 use at or near the surface of the earth. This is calculated at the surface of the earth. G is constant here, 9.8 meter per second squared. Increasing in height, obviously increased potential energy. Decreasing height, decreasing potential energy. Potential energy is zero at the surface of the earth, which is this one which we calculated through. If you take this equation, this is used for large changes, astronomical figures, satellites and others. Increasing height also leads to increasing potential energy. Decreasing height leads to decreasing potential energy. Potential energy is zero at infinity above earth, which we have just shown. Just to summarize everything in total, what I would like to share with you is that here you have seen that why potential energy at infinity is zero. We have also seen that unless we put a negative sign, and this is leads to zero, and that is why gravitational potential energy is always and always negative. If you put any value, 10 kilograms, 20 kilograms or so on, it is just going to cancel out and it is going to give you a single unit. And gravitational potential energy is this part, whereas gravitational potential is this part. Gravitational potential energy is this part, which we have just calculated and we have shown it to you. Also in the previous slides and the previous part, what I have shown is this one. Gravitational potential energy, if I take a change in height, PE equals to mgh, If it goes up, it gets a positive potential energy. If it goes down, it gets a negative potential energy. Same thing if we draw it in a graph where we are moving towards the surface of the earth. That means I'm going this way. I get a negative potential energy, that is minus 300 joules from this part to this part. If we're moving away from the surface of the earth, that is from R2 to R1, if we calculate it, we get a positive potential energy, that is plus 300 joules, which is this part. When we are moving this block away from the center of the earth, we get a positive energy. That summarizes what is gravitational energy, what is gravitational potential energy, difference between these two terms, how we can use it in terms of moving the block up and down, and also why gravitational potential energy at infinity is zero. We have shown that. Thank you very much for watching this video. Stay safe and stay happy.